I'm very happy to have Stefania Gori from UC Santa Cruz. She's going to talk to us about new accelerator experiments for dark sectors.
Okay, thanks for inviting. I'm happy to be here again. So today I'm going to talk about dark sector models and how to test them at the next generation of low energy, high intensity experiments. And this is the outlook. So the focus of this seminar will be on Fermilab dark matter. And so this is, as we see, it's an old idea. But the reason that I find it very interesting is that we have really good chances to probe this idea of Fermilab dark matter pretty broadly in the coming years, experimentally. Fermilab dark matter give us a strong motivation for thinking about models with dark sectors if we have a relatively light dark matter. And in this context, I will present a set of experiments that are very interesting to probe this idea of Fermilab dark matter. And I will compare what Fermilab can do, so the main focus will be indeed on this SeaQuest experiment at Fermilab, compared to what is the plan of CERN for the coming years. And then for discussing the physics that we can test at these experiments, I will mainly focus on two types of scenarios, dark matter scenarios. One scenario that is based on co-annihilation, where dark matter get the measured relic abundance through co-annihilation, and the other one is through semi-annihilation. So these are the two main models that I will focus on. And here are a few references that you might look at, plus some work in progress. I don't think I need to say much about dark matter. We know that most probably we are not alone, and after 2012 we still need something for some new degree of freedom. We know that we have a lot of this dark matter, but we really don't know much about it. So these are probably the main three things that we know about dark matter: that it gravitates, it is dark, and that is also stable cosmologically. And then, we are used to say, we have a lot of dark matter, and this is my fun fact about dark matter, that if you think about dark matter at electron scale, indeed we don't expect to have so many dark matter particles in this room or in a cup of coffee. So contrary to before 2012, we knew that there was something going on at around the electronic scale, and then we found the Higgs. Now, for dark matter, we don't know really the mass scale that is associated to this open problem, particle physics. And this, in my opinion, is really the main question for dark matter, understanding to what scale it belongs. So this is the question mark. But then, the interesting fact is that if you focus on dark matter that is thermal, so that was in equilibrium with the standard model bath in the early universe, then you learn that this mass scale is not totally unknown, but we learn that you should have a dark matter candidate that is not too far away from the electroweak scale. So we are talking always say about the dark matter state that is with a mass in between the MEV and the TeV scale, roughly speaking. So already this tells us that the parameter space of this scenario is quite limited. And then also we will see that also the couplings of this thermal dark matter is pretty much bounded. But for now, let's keep in mind this mass range.
Can you remind me, what is setting MEV? What's going on at MEV?
So here, in principle, could still work to have thermalization, but you have constraints for light degrees of freedom that it doesn't work anymore, basically. So you can have
nucleosynthesis or something?
Yeah, nucleosynthesis and CMB, and you have a lot of those. That it's relatively hard to go below the MEV. Maybe one can still cook up a model that avoid all these constraints, but this is maybe really constraints on experimental constraints.
Because matter domination is happening later.
That's right.
Happening after nucleosynthesis, for
That's
example.
Right. Yeah.
Okay. Okay, thanks.
How dark matter bounds? KEV?
KEV, yeah, that's what
Yeah,
I remember.
that's right.
So that's why I was asking, that's the one I usually,
Yeah.
okay, okay, thank you.
And then also what is interesting is that if we are above, say, a few GeV scale, then we are in the classic scenario of WIMPs, where this dark matter interacts directly with the WIMP interactions, and then can be thermal, can have the right relic abundance, the measured relic abundance. But if you are below, there is the famous Weinberg bound that is telling us that if we want to have an efficient enough annihilation, then we need to have a new interactions of dark matter. It can be new force or new scalars interacting with dark matter, and so on and so forth. So basically it tells you that we need to have an extended dark sector. Okay. Now, here I thought of this like thermal dark matter because we want to have it, as I said, thermal. That means that at a certain level we need to have a coupling between standard model particles and dark matter particles, otherwise it cannot thermalize in the real universe. So generically one can ask the question, since we have this coupling, and this coupling cannot be too tiny, maybe we have opportunities, we have an experimental opportunity to test, broadly speaking, of this scenario. Okay, since, as we'll see, we'll have a lower bound on this type of coupling. Of course, the numerical this will depend on the model, but what is nice is that we know that there will be a lower bound on this coupling here. Yeah, so if you focus, as I said, so the main focus will be on light dark matter. Let me spend a few words on WIMPs, first of all. And for WIMPs, as we know, we have learned a lot in the last decade, and we have experiments that were quite incredible in setting bounds and constraints on the WIMP idea. The LHC itself is a WIMP factory. If dark matter obviously is interacting with our forces with the Z interaction, so then we would produce tons of these dark matter particles at the LHC. And then also, similarly, we could have a lot of scattering between dark matter states and our detectors at direct detection experiments. And putting all together, typically we see these plots that are super highly model dependent, but somehow people like to put everything together. And in these plots, one can see the bounds on this cross-section for spin-independent dark matter nucleon. And you see the bound either coming from the LHC above here or coming from direct detection experiments. And then you can compute the cross-section that you naively expect from WIMP dark matter, and you learn that this bound here is testing something like 3 orders of magnitude or so weaker coupling than the weak coupling. Okay. That's why generically we say that WIMP models have been quite broadly explored, even though there are quite a few opportunities still. But yeah. But then you see that so generically these direct detection bounds are shooting up at lower masses, and in general here indeed if you go below a few GeV the bounds will be weaker. So this is the question I want to ask: what happens if you are below a few GeV? How do we have chances for probing this paradigm of having thermal dark matter below a few GeV in the coming years? Okay. So there are ideas for new experiments for direct detection that are kind of different than the xenon experiment and so on, but there are ideas. And what I want to push for are accelerator experiments to test this regional parameter space from few GeV below to down to MeV or so scale. We already learned that we need some extended dark sectors, so many additional particles, many, at least one. And then we want to see how to test these. Now, a small parenthesis that I wanted to open because, so sometimes you might hear, some of you might wonder, okay, why we want to have these complicated models for dark matter can be just a particle and that's it. So why this idea of dark sectors? Actually, I want to point out, so this is not really the topic of this seminar, but it's nice to keep in mind, is that there are a lot of additional motivations for considering dark sectors. So particles not charged under the standard model gauge symmetries. Models motivated by the hierarchy problem, thinking about neutron naturalness, or even extended SUSY models. Models to address the baryon-antibaryon asymmetry for neutrino masses, even for the anomalies in data. There have been quite a bit of work for addressing like B physics anomalies or G-2 with dark sectors. So there are a lot of motivations, and from the phenomenological perspective, a lot of the signatures that we discuss can arise also from this type of models, and so not necessarily only from dark matter models. So this is something that one should probably keep in mind. And that was my parenthesis. The question, of course, is if you have a dark sector, how to have access to that. And so in our Lagrangian, there are only a few possibilities that for operators that we can write down to connect one dark particle and one standard model particle at a renormalizable level. So these particles that can be exchanged between the standard model sector and the dark sector are called mediators. We have, for example, dark photon mediator or the Higgs and so on. And these three are the renormalizable operators that we can write down. Okay. And so in principle, you see, so these couplings are dimensionless couplings, so they could be as small as we want in principle. But then, if we ask for dark matter to be thermal, dark matter can interact with the standard model only through these mediators, then this coupling cannot be too small. There will be a lower bound. Okay. So what type of lower bounds we get? So again, I want to keep the discussion generic, and then I will apply to particular models. So what type of models we can write down for a dark sector? So there is one possibility in which the mediator is the lightest state of the dark sector. Okay. These are the so-called secluded models, in which dark matter annihilates simply in the dark sector to, for example, dark photon or dark scalars. So you can forget about this part of the diagram. You just look at this annihilation process here, and this is the main process that is taking care of regulating and fixing the relic abundance for dark matter. So something that happens only in the dark sector. But then, we know that, for example, the dark photon or the dark scalar interact with us, and this is the interaction that we need to have thermalization. And in fact, what we did was to compute a lower bound on this coupling here, such that we have thermalization in the real universe. And then for the specific case of the dark photon, I mean, we did the exercise for all the quarters, but this is the plot for the dark photon. We see that so this yellow region here, so this is a plot for as a function of the mass of dark matter and this function of epsilon. And basically, this epsilon cannot be smaller, say, than 10 to the minus 8 or so, if we want to have this thermalization. And this is our lower bound, so the value that we would like to test experimentally in such a way to say, okay, we have probed broadly this idea of thermal dark matter for this secluded scenario. Okay. Of course, numerically it changes if we consider Higgs boson and so on, but we get numbers that are small but not incredibly too tiny. Okay.
The green region.
So yeah, there is a difference between green and blue, namely that the green, so there was the dark matter, the dark sector and the standard model were in thermal equilibrium at a certain point, but then they went out of thermal equilibrium before a freeze out. And instead here they are always in thermal equilibrium, and here they are never in thermal equilibrium. These are the three regions that we can have.
Right. So there's a difference between the shaded lines.
So this shaded line, this you mean? So these are actually the regions where we don't trust incredibly much of our calculations because there are a lot of resonances. So we shaded them because we say, okay, there's a warning that there's a little bit more tricky here. Okay. So this was for the case of secluded dark matter, where the mediator is the lightest. Of course, we can have an opposite case in which the mediator is heavier than some other particle. A minimal model, the opposite minimal model is the model in which the mediator is heavier simply than dark matter. And then what will happen is that dark matter will annihilate directly to the standard model through shell exchanges. And in this case, obviously, the relic abundance is fixed not only by coupling in the dark sector, but also by the coupling with the standard model. So you always see plots like this that tell us where the relic abundance is the measured one. And then on the y-axis, you will always have the product of these two couplings. Okay. And then you can do your calculation for the relic abundance, and then you will get answers like this, for example, for a scalar dark matter or for a fermion dark matter. Okay. And then again, experimentally, you would like to be able to probe these lines, at least up to these lines. Okay. So these are the simplest cases that you can write down, where you have only the mediator and the dark matter. And these are the possible experimental goals that you might have. Obviously, the phenomenology of the mediator will be completely different in the two cases, because in this case, the mediator will decay mainly to dark matter, so invisible. In the other case, it can only decay back to the standard model, so with visible decays. And then there is a third option, namely that the dark sector is a little bit more complicated, so it has more than two particles. Two are needed, but maybe we have more than that. And there are many interesting scenarios, models, in which we have a third particle. I can call it, generically a dark matter excited state, but okay, it's another dark sector particle. And there are models in which the dark matter is co-annihilating with this additional particle that has a mass that is not too far away. Or models in which you have semi-annihilation, in the sense that dark matter still annihilate with itself, but it can produce, if in the early universe where we have enough energy, can produce a heavier state that then decays back to the standard model. So these are two additional scenarios, so sort of exceptions in the calculation of the relic abundance, that are very interesting theoretically, and that, as I will show, can be quite broadly explored experimentally in the coming years. And then again, thinking about phenomenology, as we've seen quite a bit of details, the mediator will decay, as you see here, because of this spectrum, to visible standard model particles, as well as dark matter particles that are invisible. Okay, so this is, broadly speaking, the type of phenomenology that we expect to have for the mediator. And and this will be the focus of this seminar. So the experiments that I want to focus on are fixed target experiments and beam dump. And the idea is, so this is a cartoon of this type of experiments. They all, so since we are all theorists, I can say that they all look similar in a very broad approximation. So we have a high intensity beam of electrons or protons. Can do the same, type of experiments with neutrino beams, obviously. Then we have here a small target that is followed by a dump, and the reason the dump is important is that it is very, very useful to shield from a lot of standard model radiation. So here all the standard model particles are blocked, apart from neutrinos and high energy muons, in first approximation. And then here we have this decay volume, where the idea is that we'll have a dark matter or dark sector particles that are propagating, and then they are detected afterwards. Now, since in the past there have been several electron and several proton fixed target experiments, we can compare the two. This is similar to LHC and LAP, namely that protons, proton fixed target, they can reach higher energy and therefore reach to larger dark sector masses. But at the same time, they have larger backgrounds. So proton beam dumps in general, they need more shielding than what electron beam dumps need. And so CERN, so first of all, in the past, at CERN there were proton fixed target experiments, so Los Alamos and so on and so forth. And then there is the idea in the future, again at CERN, to have proton beam dump experiments. And these are the two proposals that we have nowadays. One is for the NA62 experiment that will be running in beam dump mode around 2021, 22. And then there is the proposal for a much bigger and more expensive proton beam dump experiment, that is the SHIP experiment. And this, if everything goes well, will be running in late 20s. And then there are additional proposed experiments that are in the same context, namely Codex B, Phaser, and so on. And so this is the CERN effort, and the idea will be to use this high energetic SPS beam of 400 GeV. But then we know that Fermilab itself, even if Tevatron is not running anymore, has a high intensity and high energy proton beam. So we want to see what we can do there. In the last few years, as you will see, there is this facility that is running. So this is the accelerator complex of Fermilab. This is the 120 GeV proton beam. And there is an exit that is collecting something like 5% of this proton beam, and leading it to this SeaQuest experiment, that is a nuclear physics experiment to measure the SeaQuest content of the proton at large Bjorken X. That's the reason of the name. And but then you see the cartoon. It looks really like a proton beam dump experiment. So this is the dump. This we have 5 meters of iron that is magnetic, and then afterwards here we have the detector. So these are some tracking layers that are able to reconstruct very well muon tracks. And okay, here there are some technicalities about this experiment. I think the most important feature here is that this experiment is quite compact. So overall, this dimension here is 25 meters, and this is only 5 meters. And the idea is that we have a dark particle that is produced here, the target, then it's a little bit long-lived, and then it decays after the dump, but the lifetime should not be too long, in such a way to survive the dump and then decay afterwards. And this is actually quite different than, for example, the SHIP experiment, where the length in the game are quite longer. So the idea is that this experiment, as we see, will be quite complementary, because we'll have access to lifetimes that are long but not incredibly too long, contrary to other past experiments and proposed experiments.
What about, I had the impression that Codex was actually becoming more on shell, and they were also smaller, right? Do you know how they compare to yours?
That's right. So it's a bit different because Codex B is a bit off axis.
Mm-hmm.
So we have a proton beam. So this is close to the LHC detector, but off axis. And then obviously the energy is also different because these are the proton beam of the LHC.
So it's going to go for more heavy stuff, right? You're going for lighter stuff that's got to be forward.
That's right, forward, and less displaced as well, actually. Yeah,
Okay.
that's right. Yeah, I should probably put Codex B here as well. Yeah. Here is a little bit of history of this experiment, but mainly the message here is that this was a relatively old experiment, not super new, but always used in the context of nuclear physics, and only lately there have been some, more enthusiasm of doing particle physics, and there have been already some upgrade of this experiment for doing particle physics. Namely, was this installation of a displaced muon trigger, because at the beginning, basically, what this experiment could do was only to reconstruct muons coming from the target, and all the rest was thrown away. Now what it can do is also to reconstruct muons coming from after the dump. Okay? And this is some upgrade that have been done 2 years ago or so. And then now hopefully it will collect data again soon, in the next few months or so. There should be another phase of the experiment starting, with the idea of collecting a lot more luminosity, something like 10 to the 18 protons on target. It is quite a bit, over the period of 2 years. And then what is, in my opinion, even more interesting is the possibility of having additional upgrades of the experiment. The reason being that now what they can do is to measure super well muons. And they can say, okay, this is a muon, this is not a muon, but they cannot say this is an electron, this is a pion, and so on and so forth. So what we would like to do is to have upgrades, for example, to putting an electromagnetic calorimeter, such to be able to identify a lot more particles very well. So that we'll have access to these additional signatures with electron, pions, photons, and so on and so forth.
Sorry, I know you said it, but what kind of detector do they have right now? What can they detect right now? I'm sure you said it, but
So these are just tracking stations here. So this
they're
is
just
just a
charged
tracker.
particle trackers.
That's right. And then afterwards here they have an absorber wall. And if you have a track that is reaching that, then they say that is a muon because it's quite penetrating. That's why they can say if it is a muon or
So
not.
that's why they don't need they don't have any magnetic field or anything else. They just anything that reaches the end they assume is a muon.
That's right, but they do have also magnetic fields actually, and this is mainly for momentum measurement.
Yeah.
And so this red thing is a magnet, and then also the dump is a magnet, and this is mainly for getting read better of the background. Yeah.
But that doesn't give you enough discrimination for pions and muons, magnetic field.
Pions, yeah, you can see if you have a track that is a muon or not, but you cannot say if it is, for example, an electron or a pion.
Okay.
That is the main
It's
problem.
the lighter particle
That's right.
discrimination.
Yeah. And then, of course, you don't see photons, for example. And,
Right.
Okay, yeah, here just briefly, so obviously if you have access to electrons or pions, you can test a lot more dark sector models, light dark sector models where the mu decay is kinematically closed, or as we see, squeezed dark sector models, models that are hadronically decaying. There are a lot of opportunities to, for new measurements if you have these upgrades. And this is something that we are working quite a bit on nowadays, with more universities that joined recently in the particle physics community, not nuclear physics anymore. And that's why there was the idea of we are changing the name, speaking of names, so to call it the DarkQuest instead of SeaQuest.
So tell them that in the Midwest, the dark is much closer than the sea.
We should write it in our proposal. So now let's focus on models and see what type of interesting models we can study. And so the main focus will be on this, as I already mentioned, models in which you have co-annihilation and model for semi-annihilation. And the models that I will discuss are models based on the dark photon interaction. So this is the only interaction between the dark sector and the standard model. And I will comment a little bit about going beyond dark photons. But, yeah. So first of all, why dark photon models? So dark photon is one of the three portals that we have. And then also, dark photons are very, very nice for proton beam dumps. The reason being that we produce tons of them. So there are several production modes for dark photons. The main ones are Bremsstrahlung and also meson decays, including heavy mesons. I mean, heavier mesons, so not only pions, decays, but also eta, omega, eta prime, and so on. And we see that even if this kinetic mixing operator is small, so here I'm putting 10 to minus 6, we still have a production of millions of these dark photons over a broad range of parameters. So that sort of starts well, since we have a large statistics. Much larger actually than electron fixed target experiments. This is the corresponding line for the same energy and same luminosity.
Sorry, oh, I see. This is a number for a fixed, instead of luminosity, you said protons on target.
Yeah, that.
Right.
Yeah,
okay, I got it.
Yeah.
Thanks.
And then as a warm-up, what we have done is to compute the reach of this experiment for a minimal dark photon model, or in the language we were using before for these secluded dark matter models, in which the dark photon is the lattice state. And so this is the reach that we have at SeaQuest, and so always when we discuss beam dumps, we have a reach that looks like this. And the reason being that if you go towards lower values of epsilon, we have some displacement, so the dark photon will have a long lifetime, and this is the lifetime plot as a function of its mass. We see for epsilon 10 to the minus 6, indeed, we have a lifetime close to a meter or so. That is the sweet spot for SeaQuest. And then also you see that, so these gray, almost invisible regions are the regions probed in the past. We already mentioned CHARM, and CHARM was a much longer baseline experiment. That's why you see that these curves are towards lower values of epsilon, larger displacement. And this is the result for the two luminosities. So the approved luminosity of 10 to the 18 and the sort of futuristic luminosity of 20 to the 20. So to see how much we can improve. And what is interesting is that indeed this reach goes towards larger values of epsilon, and this is the region that is typically the most difficult to be probed, because we have a little bit of displacement, but not very much.
So is that, yeah, I was just wanted to ask about that, maybe, that sort of, I don't know, nose or whatever, that wedge up in that region right there. Epsilon is pretty big.
Yeah.
The mass is really small. And so it's just, what's going on in there that makes it so hard?
So for beam dumps, it's hard because you don't pass the dump. So I mean.
You make a lot of these things, presumably.
Right. But then you have an exponential
right.
decay, so they get stuck in the dump basically.
But you make more of them, so somehow you could try to have. I don't know what you would do with all the other crap, but you could try to, okay, but I understand, okay.
Yeah, because the rate goes like epsilon square.
Yes.
But then the lifetime is like an exponent, so it's hard to, beat an exponent with a square, no? That's why it's just hard, even if you collect more data, to really go in this direction.
What is the exponent you're comparing to? I just want to understand.
So the lifetime of the dark photon.
Right.
And that enters like an exponent if you require to be decaying afterwards. And instead the production, so the production that we saw here, this production scale like epsilon squared times the mass.
Right. Yeah, right. Okay. Yeah, I understand.
So
you're saying you need some minimum distance, if you're doing a classic beam dump anyway, you need some minimum distance just to get rid of all the other stuff.
That's right.
And then you just don't have any of these guys left.
Right. And then, you could think about going down from here, from prompt searches like Babar and so on, and like Bell 2 will go a little bit down by a factor of a few. But then again, you start to be limited by cross-section. Here, maybe no, I don't think I have a backup slide, but here there are a few regions, maybe I do, let's see. No. Okay, there are a couple of regions here of LHCb actually from meson decays. That LHCb is very good in looking for displacement that are super tiny, and that's why LHCb here could do something, but only at low masses. Yeah.
Okay, thanks. Yeah.
What is this, the tip on the feature?
Oh, this was so the dark photon mixes with what is in the raw meson. What is so you have a mixing effect that is enhancing the production. That is the same as this thing here. And then also here there is the comparison with other machines that have been proposed. So the NA62 experiment we introduced before, SHIP, and also there is phaser. The reach is very, very close to phaser, but this is phaser that, so with the high luminosity. So the phaser is another facility that is being proposed using the LHC beam. And here they need 3 inverse orthogonal data. And then we have an A62 towards lower values of epsilon, and SHIP that is the big machine that will probe a lot, but later on. And then also in terms of dark matter models, so if you remember, we saw this lower bound on epsilon coming from thermalization, and the lower bound was indeed at 10 to the minus 8, roughly speaking. So this is what is written here, that all this plane here is highly motivated by these secluded dark matter scenarios, and all of them are thermal. So it's nice to see that we can reach this 10 to the minus 8 in the future with SHIP. So this was a sort of warm-up with a very simple model. And then there are 2 more models that I wanted to discuss with you, this co-annihilation, semi-annihilation model. So for co-annihilation, the idea is simple, that you have these 2 states that are annihilating together with obviously the cross-section is large enough if the mass splitting is not too big, otherwise this process will be suppressed. And these type of models can be realized in elastic regime, in which you have a mediator that is talking in an off-diagonal way to the dark matter and the dark matter excited state. And this inelastic idea was proposed some time ago to address some anomaly, this dumb anomaly in data. And then it's also quite interesting because, so cosmologically, this is pretty much open, in the sense that this chi2, since it decays, to decay to a chi1 and the standard model, then it can be depleted sufficiently such, before recombination, such that the CMB constraints are pretty weak. Okay. So even if we have a light objects, CMB, we are quite fine with CMB. There are several models that you can write down to realize this idea, and what I will analyze are models that are based on a new U1 symmetry.
Sorry, can you just go back to that point? I realize I didn't understand that. My very crude understanding from what you said before was that in this light dark matter case, it's that matter domination happens too late. So why is it helping me that you're imagining that it's freezing out, you're getting matter domination before CMB, but then it shouldn't matter. I'm just confused, because then it shouldn't matter if they decay. Whereas if matter domination is happening after CMB, again, I don't see why, I guess I just don't understand why it matters that one of them can decay.
So what one wants, in general, is that before, that this process is shut down at the time of CMB. Because otherwise what will happen is that this process give some...
Right, you want matter domination to start before the CMB, but that doesn't mean you want the mass of these guys to be heavy enough.
Yeah, either heavy enough.
You're saying that the heavier guy is then setting the onset, is that the point? Or?
No,
decaying before it.
That's right.
But then,
So
how
CMB,
do you get to matter domination? You need to deplete the light guy, let's say X1, who's the light guy who's really going to be the dark matter. You need to deplete its relic abundance.
But this is earlier, right?
X2 is dark matter?
No, X1 is,
Yeah.
Chi1 is dark matter.
That's right.
Chi2 just decay to Chi1 plus
Right.
similar.
So what you want to have is that at the time of CMB, I
Oh.
mean, matter, you know,
I guess I was confused. You said co-annihilation on top, and it's happening by decays at Chi2.
no, not really. So
No.
there is,
Okay.
so in terms of setting the relic abundance of this Chi1, this
Yeah.
is the process.
So you
is,
drop below the mass of Chi2, right? And then,
that's right.
but then this is strong
Then
enough.
you have Chi1, Chi2 freeze out. Then
That's
right.
Chi2 eventually decay to Chi1.
That's right. So after it frees out, Chi2 decays, because it can decay to Chi1 and the standard model.
Why is that better than just having Chi1 freeze out at that same? I don't understand why that weakens cosmological constraints, because if there was just Chi1 and it was annihilating instead,
Chi1 doesn't annihilate. It
it's that,
It
okay,
has to
we
annihilate
don't call
with
that
Chi2.
annihilation, but that diagram
That's co-annihilation.
co-annihilates,
Right.
okay, co-annihilates. I'm saying compared to a model where Chi1, where there's just a Chi1 and I have the same diagram except where Chi2 is replaced by Chi1, I don't see a big difference.
Well, then you wouldn't explain Dama. That was
No,
Yeah,
okay,
I don't
this
care
forget
about
about it.
Dama.
But
I
I
don't
mean,
care about Dama.
indeed, if you have a
Nobody does.
Chi1 here,
Yeah.
and then this process always goes,
Yes,
even at the time of CMB,
yeah.
and then because of this standard model,
I agree if it was going at the time of CMB,
Right.
but I guess I just don't understand that somehow, I think it's okay.
so this is a
I
sort
didn't
of
understand your point that somehow co-annihilation versus annihilation was somehow better for CMB. It seems like in both cases you just need to make sure that it happens, matter domination occurs
Sure,
before
yeah, if you have
CMB
a,
temperature.
yeah, but this is one way of getting it, right? But then at CMB, since this guy doesn't exist anymore, because it's all decayed, then you don't have to worry.
Right, but in any case you have to make that guy light enough that
Sure.
matter that this process is efficient
Yeah.
at making Chi1 have
No,
the right
it
relative
doesn't
balance.
matter. Sorry, if they are very light, if Chi1 can still annihilate with a small rate, that's still affecting CMB
That's
data.
right.
Ah, I
So
see.
the
I see. So it's shutting off compared to a
Yeah.
model with just Chi1,
Exactly, yeah.
it's more efficient at shutting off the residual annihilations that can affect the CMB.
Yeah.
For
that's right.
S-wave
Okay.
Yeah.
below 20 GeV.
That was the point
That's
I
right.
was missing. Okay, thank you.
Okay.
good. Yeah, that's what I was missing.
Yeah, and then there is a quite simple model that one can write down in which you have these two states that are charged under this U1, and then the way in which you get this inelastic interaction is because indeed you have in general these Majorana masses are breaking this U1 symmetry, so it's kind of natural to think that these Majorana masses are smaller than the Dirac mass. And then we see that actually the elastic interaction is suppressed by this ratio of Majorana versus over Dirac mass. So this is just a way to get this inelastic regime where dark photon talk to Chi1, Chi2 off diagonally, and then also because of this symmetry, we expect that the mass splitting between Chi1 and Chi2 is small. Okay, what I call delta. And so what's the phenomenology of a model like that? So this is my spectrum, and here it is where I go to the standard model. And then what happens is that the dark photon, the mediator, will decay diagonally to Chi1, Chi2. And then the Chi2, what is interesting is that it decays, as we have already discussed. But this can be very long-lived because this width is suppressed by the fifth power of this mass splitting. And indeed, you can compute the lifetime of this Chi2. And so in this plot, I'm showing as a function of mass of dark matter and epsilon the lifetime of Chi2. So these are these dashed lines to benchmark models, if you want, with 5% mass splitting and 10%. And then the lines that reproduce the right relic abundance. Okay. And if you read the numbers, you see that indeed the Chi2 is quite long-lived, at least a few meters. And then the idea at the fixed target would be to produce the dark photon and then follow this decay chain, and then to look for electrons in the final state. So what we have done is to focus on the regime in which the relic abundance is the measured one. So this dark matter state is the full dark matter story. So we fix epsilon as a function of the mass, and all the parameter space is shown in this plane here, where you have the degree of freedom, the alpha dark, that is the coupling between the dark photon and dark matter, and the mass of dark matter, as well as we need to fix the mass splitting, for example, 10%. And what is interesting here, again, the color are a little bit fading, but so these gray regions here, so there is a region here and then a region here. These are past experiments. It's quite interesting to see that a lot of regions have been already probed. So there is Babar. This was a monophoton search by Babar, with the idea that this Chi2 was escaping the detection. Then we have all the fixed target experiments, and then also fixed proton beam dumps with dark photons coming from pion decays. So these are the 1, 2, and 3 regions here.
Sorry, so alpha dark is proportional to the epsilon, or? Sorry, maybe I've got
it goes like 1 over epsilon square. So the relic abundance scale like epsilon square alpha dark times a lot of stuff. That's why, yeah.
Because I'm trying to understand, because why exclusion things are going up now in this plot. That's because this thing is going like 1 over
epsilon square. That's why. That's right. So yeah, in general, large alpha dark.
There isn't. I can't really see your gray. There's nothing up there, right? There's no gray up there.
Yeah, there is only this that we wanted to put the condition at alpha dark. Yeah, there is some running, and alpha dark is not too large, but otherwise there is nothing. Precisely because epsilon is super small there.
Okay.
Yeah, and instead here there is much more stuff because epsilon is big. So it's the reverse thing. Yeah. And and then again, the idea is to look for these decays at SeaQuest, either to electrons or muons, and then actually we could probe everything between these lines, depending on the luminosity. So for 10 to the 18, we are between this line here and this line here, and then this is 10 to the 20. And then also what is interesting is actually that since we are thinking about squeezed regimes such that the co-annihilation is efficient, then if you just look for mu plus mu minus, as SeaQuest can do now without any upgrade, then we would have available only this region here of parameter space, because otherwise here this is kinematically not allowed.
Is the LDMX to the left?
Yeah, that's right. I should have mentioned. Yeah, LDMX is towards the Latin masses. Yeah.
So I still don't know how to read this plot. The LEP is excluding what?
Yeah, this thing here. So this is.
That's the LEP is labeling that a shaded thing that I can't see.
Yeah, that's right.
Yeah. Okay. No, I just then what are these lines that almost cover the whole space?
These lines
No,
here?
no. Around the whole frame, the dashed lines that are going all.
Those are the SeaQuest lines.
Yeah,
okay.
these are the SeaQuest
Oh, that's
lines.
SeaQuest. Okay,
So
that's
there
your
are
point.
4 lines of SeaQuest, and the reach is in between the lines with the same. Yeah,
Okay, I understand. And with more luminosity,
that's right.
more protons.
Yeah, that's right.
Okay, thank you.
Yeah, my laptop, the gray is very dark, but here is very good.
Right.
Anyways, so basically the message is that with SeaQuest we could probe up to a few GeV, because then, so I have to say that below 10 to the minus 2 GeV, these models are not really working too well anymore, so we are squeezing everything. And therefore, basically, the region of parameter space that is really important is about 10 to the minus 2 roughly, and then we see that we could probe up to 4 or 5 GeV with SeaQuest entirely. Of course, the caveat is that if you go to super squeezed, then it starts to be harder and harder, as we know.
Just because the lifetime's getting longer.
Yeah, lifetime longer, softer electrons and muons. It's like for the LHC that squeezed scenarios are always tricky. But 10-5% is good. Below 5% start to be tricky.
Does LDMS do anything if we do have the SeaQuest cover?
Yeah, so LDMX to test from here down. So there is a white region that is also possibly testable by LDMX. I didn't mention this experiment, but this is another proposed experiment for missing momentum.
And it goes way even further down.
Yeah, it doesn't. Yeah, that's right.
Okay. What is LDMX? What type of experiment is it?
This is an experiment proposed for SLAC with an high-intensity electron beam, and the idea is to measure the scattered beam, so that if you produce something that is invisible, whatever you produce, then you measure it through the measurement of the electron that is recoiling. So I didn't mention because this is for invisible signatures of anything that you imagine, and I'm focusing on more visible for SeaQuest.
That's it proposed by the field and target.
That's right. And so I'm running out of time, so maybe I mention you have to leave, but so I mentioned
We're
this.
asking a lot of questions, so take a few extra minutes.
So I want to mention the last scenario. This is semi-annihilation scenario. So this is SVC is connected to this idea of SIMPs, of strongly interacting dark matter models. So SIMPs have been introduced to have processes like this, 3 to 2, that are fixing the number density of dark matter instead of the classic 2 to 2 for WIMPs. And so one possible realization of this 3 to 2 process is to take a QCD-like dark sector, and then thanks to this, you can do it generically with some number of flavor, and then you have this symmetry that is broken and giving rise to light pions. And these light pions are the dark matter candidate of this QCD-like dark sector. And then these pions can have this 3 to 2 annihilation thanks to this less zoom in a bit in the Lagrangian. So that's the idea. Of course, again, if you want to have thermal pions, you will need some connection between the two worlds, and you can do it with a dark photon, or there are many investigations in the literature for axion mediation or a dark scalar and so on and so forth. And then again, this cannot be too small if you want to have a thermal scenario. And so why semi-annihilation? I'm talking about the 3 to 2 process. And the reason is that what we have discovered is that in these models, since the region that is interesting from these models is the region where m-pi over f-pi is large, automatically you also have large semi-annihilation process with additional states in the dark sector like the dark vectors, what I call here BD. So dark vectors have a mass that is not too far away from the pion mass. Of course you have some degree of freedom, but parametrically they are not too far away from the pions. And then at early enough universe you can have also this process that is very important. And this is taking care of depleting the number of pions because the dark vector actually decays back to the standard model. For example, a dark vector can mix with a dark photon, or also you can have off-shell decays and so on. Okay. So this is an interesting process that we have to consider when we compute the cosmological history of these pions. And then, of course, if this epsilon is not too small, then you can have the classic annihilation of the pions into standard models, also this process. So all of this should be considered when we compute the relic abundance. And this is the answer that we get. So the 4 lines are computed for different ratios between the dark vector and the dark pion mass. And as we expect, we will have quite a bit of dependence on this mass ratio, because this semi-annihilation is more or less efficient depending on the masses. And then we see the 3 regimes, right? That if epsilon is big, then this will be the dominant process, and we have this WIMP-like type of behavior. If you go to lower values of epsilon, then this semi-annihilation is the important process. Here you don't have any more epsilon dependence, because if epsilon is big enough, then this is efficient enough that it all decays to the standard model, so you don't have epsilon dependence. But then again, if epsilon start to become smaller and smaller, both of these processes are more and more suppressed, and then you're left with this 3 to 2. That obviously doesn't depend on epsilon, it's just the best Zumino-Witten term, and then you are fixing the mass for this dark matter that you need. Okay. So this is the overall feature for these models, and these again, these lines are the target that we would like to probe experimentally.
Here you fixed the lambda QCD scale or something? You fixed F pi basically?
Yeah, so we fixed the ratio, we fixed F pi, yeah. So in the plot we have this ratio, and yeah, that's right. And then what about the phenomenology? So now the mediator has an interesting phenomenology, because so we have a spectrum like this, okay, and then the dark photon can decay either to dark matter, an invisible decay, or to a dark matter state and the vector state. Branch ratios, we have some dependence on m pi over f pi, and we see that for m pi over f pi that is not too small, indeed we have quite a bit of decay into vectors. And then what happens is that the vectors, either they follow a two-body decay if they mix with a dark photon, or they have a three-body decay for example, the charged vectors. And then we have, actually we can compute the lifetime, and we see that the dark vectors are generically long-lived again. And therefore, we can already guess that this is a good scenario for beam downs, okay? Because we have these long-lived particles produced from dark photon decays.
You're kind of assuming that you can use QCD
Right, yes.
models that fit the data as a good guide to the masses and couplings of the resonances.
That's right, that's right. Yeah, correct, yeah. And then this is again our reach, so this mass of the dark photon and epsilon, and these are the lines for the relic abundance. For example, we're fixing this ratio 1.6, there was the 1.9 here, so generically the lines are around here. And then again, the gray regions are regions from past experiments. We have again Babar, this Ian 37 that was another fixed target electron experiment. And then we see the SeaQuest reach. This particular shape is because basically we have two regions, either for free body or two body, that are coming together. That's why we have these two sort of lobes. And then we see again that we can have a good sensitivity, including these lines for the relic abundance, as long as we are not too squeezed, because if we squeeze more and more, these are shifting towards higher masses. Very good. So this is what I wanted to present. So this I will skip. So I just wanted to say that so we are at the stage of looking at models that are not necessarily dark photon mediated, because in this seminar we have just discussed dark photon initiated processes. So we are looking at models where you have the scalar or neutrino portal as well as the axion portal. Skip a couple of things. Here, I just wanted to point out again that there are many new signatures that we can explore beyond the signatures that we have discussed during this seminar. For example, at SeaQuest, we could look for signatures like this of electrons and pions or kaons coming from right-handed neutrinos, or photons coming from axion-like particles. There are a lot of more things that one can do once that we have this electromagnetic EM Kala grid. And this leads to my conclusions. So what I wanted to show, first of all, is that these thermal scenarios for dark matter are quite interesting because they have a range of parameters that is pretty much bounded, both in mass and couplings. And then specifically there are classes of models that we can study, these secluded, co-annihilation, semi-annihilation models, that give us all a target, an experimental target to reach, in such a way to probe these scenarios broadly. And so these models are interesting, and then there is a good opportunity to test them at this SeaQuest experiment. And this is, I want to leave you with this time scale. So there is this proposal that we are, SeaQuest, the SeaQuest as it is, it will be running now-ish, looking just for muons. And then afterwards, hopefully, there will be this upgrade with the electromagnetic calorimeter. And then this is the comparison with the experiment proposed at CERN. And as we mentioned, I should also put this codex B and phaser. That's it.
Have any other questions?
So the dark class is being proposed, and what's the status? Is it going to be approved or anything?
Yeah, so there is, so we are working, so there has been a DOE call for basic research need experiment for dark matter. And so we are working on the proposal, and we should get to know it in a short time scale, like in a year or even less time scale, at least in the context of this proposal. And then this is something that, as I said, if it happens, hopefully it will start running, say, in 2021 or 22 or so, because now there is this other phase of the experiment that has to be run, that has to run. But this will look just for muon signatures. And then hopefully afterwards we'll be able to look for many more signatures for dark sectors. But at least this, I think that at least in the context of SeaQuest with muon signatures, hopefully there will be analysis coming out in the coming couple of years with the luminosity collected starting from a few months from now.
So this proposal together with the SeaQuest collaboration? Or
yeah, that's right. So it's...
they are happy to have it to extend it for some while.
Yeah, so SeaQuest, the collaboration is mainly done by nuclear physicists, and this is a collaboration, I think, of 60, 70 people or so, so this is pretty small. And maybe other 10 people are also interested in particle physics. And then, so we are collaborating with this order 10 people of the collaboration that are interested in particle physics. Plus, also there are, let me go back. So there are additional people that are not in the SeaQuest collaboration that joined for this proposal for continuing a particle physics program in this experiment.
So the other 50 people, are they okay with you taking over?
Yeah, it can be tricky because some don't have really a background in particle physics, so they want to measure PDFs. But it's true that, their program, the nuclear physics program has been approved until 2021, and they have this last phase that has been approved with polarized target, and beyond that they have no other proposal for continuing the experiment, so we can take that.
there are no other questions, let's thank Stefania again.